There's no reason for it to stop, although it might come in spurts. And this restless Yellowstone caldera is truly living, breathing. Every once in a while, it burps.
Deep beneath America's most famous national park, a silent transformation is taking place. Recently, the United States Geological Survey raised eyebrows when they issued an alert about a dome-shaped uplift forming in Yellowstone National Park. This mysterious bulge growing slowly but steadily beneath the park's surface has captured the attention of scientists and sparked curiosity and concern among the public.
Natural systems can throw us a lot of curveballs. A lot of things can happen that we're not really ready for.
But what exactly is happening beneath Yellowstone's picturesque landscape? Is this dome a harbinger of something catastrophic or simply another chapter in the park's dynamic geological story?
These eruptions are enormous. The amount of material erupted from them, huge.
To understand the significance of this development, we need to dive into the fiery heart of one of nature's most powerful forces, a supervolcano that has shaped the North American continent for millions of years. To grasp the significance of the recent alert, we first need to understand what makes Yellowstone so unique. Unlike traditional cone-shaped volcanoes that dot our planet's surface, Yellowstone hosts something far more massive, a supervolcano. But what exactly does that mean? Imagine a volcanic system so powerful that when it erupts, it doesn't build a mountain, it collapses into itself, forming a massive depression called a caldera. Yellowstone's caldera spans roughly 30 by 45 miles, large enough to swallow entire cities. This enormous volcanic system sits atop a hotspot, a place where a plume of magma rises from deep within the Earth's mantle, creating a persistent heat source that fuels the park's famous geysers, hot springs, and bubbling mud pots. Yellowstone has experienced 3 cataclysmic eruptions over the past 2.1 million years. The most recent major eruption occurred approximately 640,000 years ago, ejecting enough material to bury large portions of the United States under ash and dramatically alter global climate patterns. These aren't just big eruptions, they're among the most powerful geological events on Earth. What makes Yellowstone particularly fascinating is that it's still very much alive. The ground beneath the park breathes, literally rising and falling like a sleeping giant's chest. Scientists have documented cycles of uplift and subsidence throughout the caldera over decades of monitoring. This movement reflects the dynamic nature of the magma chamber below as pressure builds and releases in an ongoing geological dance. The recent alert system announcement. In early 2023, the scientific community's attention turned sharply to Yellowstone when the United States Geological Survey, USGS, issued a formal notification regarding a dome-shaped uplift in the park's northeastern section. This wasn't a dramatic emergency alert that made front-page headlines, but rather a calculated update within the scientific monitoring community that quickly captured wider attention as the implications became clear. The alert, issued through the Yellowstone Volcano Observatory, YVO, detailed how ground monitoring instruments had detected an accelerating rate of vertical displacement in an area spanning several square miles. What particularly concerned scientists was not just the uplift itself. Yellowstone has experienced ground deformation before, but rather the rate and persistence of the growth. According to the data, certain areas were rising at rates of up to 15 centimeters, about 6 inches per year, significantly faster than the historical average of 2 to 3 centimeters annually. Dr. Charles Peterson, lead geophysicist at the YVO, explained in the alert briefing, "What we're seeing is unusual enough to warrant increased attention and monitoring resources. While this doesn't signal an imminent eruption, it represents a significant deviation from the baseline behavior we've documented over the past several decades." The alert triggered an immediate response within the scientific community. The USGS elevated Yellowstone's monitoring status from normal to advisory, the second level in their 4-tier volcanic alert system. This designation indicates heightened unrest above known background activity, but doesn't suggest that an eruption is likely or imminent. Within days of the announcement, additional monitoring equipment was deployed to the affected area. Mobile seismic arrays, precision GPS stations, and gas sampling equipment were all brought to bear on the mysterious bulge. The National Science Foundation fast-tracked funding for additional research, and satellite time was redirected to provide more frequent observation passes over the region. What made this alert particularly significant was its timing relative to other volcanic indicators. The dome's growth coincided with a subtle but measurable increase in both seismic activity and ground temperature in the same region. This trinity of warning signs, deformation, seismicity, and thermal changes represents what volcanologists consider a potential precursor pattern to increased volcanic activity. Anatomy of the dome-shaped uplift. What exactly is this dome that has scientists so intrigued? Visualize the Earth's crust as a flexible layer, similar to the skin on pudding. When pressure builds underneath, this skin can slowly bulge upward, creating what geologists call a resurgent dome. The current Yellowstone uplift is precisely this type of formation, spanning approximately 7 miles in diameter and centered in the northeastern section of the caldera. The mechanics behind this phenomenon involve complex interactions between magma, gases, and the overlying rock. The primary driver is usually one of 3 processes: magma intrusion, hydrothermal fluid accumulation, or gas pressure buildup. In the case of Yellowstone's current dome, evidence suggests it's likely a combination of these factors at work. When magma rises from deeper reservoirs, it can accumulate in shallower chambers, creating upward pressure on the rock above. This process, called magma intrusion, effectively pushes the ground upward like air inflating a balloon. However, the current uplift doesn't necessarily mean fresh magma is flowing in. It could instead represent the expansion of existing magma as it releases dissolved gases or heats surrounding rock. The hydrothermal system plays an equally important role. Yellowstone sits atop an enormous network of underground water channels that become superheated by the underlying magma. As these waters heat, they expand and can become pressurized, especially if mineral deposits seal off natural venting pathways. This pressurized system can literally jack up the landscape from below. What makes this particular dome formation especially interesting is its structural composition. Ground-penetrating radar and seismic tomography reveal that it isn't a simple uniform bulge, but rather a complex structure with varying densities. The dome features a central core of lower-density material, surrounded by zones of more rigid rock. This suggests that whatever is causing the uplift isn't just pushing upward, but is also changing the physical properties of the surrounding rock. Temperature measurements taken at the surface show subtle but measurable increases directly above the dome, approximately 2-3 degrees higher than historical averages for the area. Gas emissions have also changed, with slight increases in carbon dioxide and hydrogen sulfide detected at fumaroles within the uplift zone. Measuring the increase. How do scientists actually track something as subtle as ground movement that might only amount to a few centimeters per month? The answer lies in an impressive array of monitoring technologies that provide unprecedented precision in measuring Earth's movements. At the forefront of these tools is interferometric synthetic aperture radar (INSAR), a satellite-based technology that can detect ground movement with millimeter-level accuracy. By comparing radar images taken at different times, scientists create colorful interference maps that reveal areas of uplift or subsidence. For Yellowstone's dome, these INSAR images show a distinctive bullseye pattern, concentric rings of color that indicate the ground is rising most dramatically at the center of the dome and tapering off toward its edges. Complementing this bird's-eye view is a network of continuous GPS stations anchored directly into Yellowstone's bedrock. These stations, part of the Yellowstone Geodetic Network, transmit data in real time to monitoring centers. Each station can detect position changes as small as 1 millimeter, providing a 3-dimensional picture of how the ground is moving. According to Dr. Melissa Chen, geodesist with the USGS, the GPS data has been invaluable in showing us not just vertical movement, but horizontal expansion as well. The dome isn't just rising, it's stretching outward. The measurements tell a compelling story. When the uplift was first detected in early 2023, the central portion of the dome was rising at approximately 7 centimeters per year. By mid-year, that rate had increased to 15 centimeters annually, a significant acceleration that triggered the alert. At certain GPS stations within the dome, the cumulative uplift has now exceeded 30 centimeters from the baseline established in 2020. Beyond simple elevation changes, scientists track the dome's volumetric expansion. Current estimates suggest the volume of the uplifted area is increasing by approximately 0.05 cubic kilometers per year, meaning something beneath the surface is creating space where there was none before. Tilt meters provide another crucial measurement perspective. These instruments, essentially high-precision carpenter's levels, detect subtle changes in ground slope. The current dome shows a distinctive tilt pattern, with the ground sloping away from the center in all directions, but with slightly greater tilt on the eastern flank, suggesting asymmetrical forces at work beneath the surface. Perhaps most telling are the strain measurements. Strain meters buried deep in boreholes measure how rocks stretch or compress. Data from these instruments reveals that rocks within the dome are currently under significant tension. They're being stretched as whatever is beneath pushes upward and outward. This tension creates microfractures that can be detected as tiny earthquakes, providing yet another data set for scientists to analyze. Historical context of Yellowstone uplifts. Yellowstone's current dome formation, while concerning, isn't unprecedented. The park's geological history reveals a pattern of uplift and subsidence events that provides valuable context for understanding the present situation. By examining these past episodes, scientists can better interpret what today's measurements might mean for the future. The most significant documented uplift period began in 1923 and continued until 1984, during which the central caldera rose by nearly 90 centimeters, about 3 feet, over 6 decades. This long, slow inflation was followed by a period of subsidence when the ground actually sank by about 14 centimeters between 1985 and 1995. Then another uplift phase began, creating what scientists now call a breathing pattern to Yellowstone's geological behavior. Perhaps the most relevant historical comparison comes from the 2004-2010 period, when an area near the current dome experienced dramatic uplift rates of up to 7 centimeters per year. During this event, the Yellowstone Volcano Observatory also issued an advisory notice, and many feared it might presage an eruption. However, after several years, the uplift gradually slowed and then stopped entirely without any volcanic activity. Scientists concluded that the event was likely caused by the migration of hydrothermal fluids rather than magma movement. What's particularly instructive about the 2004 event, explains Dr. Robert Williams, a USGS volcanologist who witnessed that episode, is how it demonstrated the caldera's ability to accommodate significant pressure changes without triggering an eruption. The system has built-in pressure release mechanisms we're still coming to understand. Even further back, geological evidence preserved in lake sediments and mineral deposits tells us that Yellowstone has experienced dozens of major uplift events over the past 15,000 years. Tree ring studies from old-growth forests in the park reveal that some areas have risen and fallen repeatedly, with trees showing stress patterns during rapid uplift periods. What makes the current dome different from these historical precedents is its location and rate of growth. Unlike the central caldera uplifts that characterize previous events, this dome is forming in the northeastern section of the park, an area with less historical deformation. Additionally, the acceleration rate exceeds what was observed in previous episodes, though it hasn't yet matched the total cumulative uplift from the 1923-1984 period. The historical record also provides reassurance. None of Yellowstone's many documented uplift events in human history has led to a major eruption. Most eventually stabilized or reversed themselves as pressure systems found equilibrium, or as magmatic fluids found pathways to release their energy through the extensive hydrothermal system. Magma chamber activity beneath Yellowstone's picturesque landscape lies one of the world's largest magma systems, a complex network of chambers and reservoirs that fuels the park's famous geothermal features. The relationship between this magma system and the surface dome is central to understanding what's happening and what might come next. Recent seismic tomography, essentially CT scans of the Earth's interior, has revealed Yellowstone's magma system in unprecedented detail. What was once thought to be a single large chamber is now understood to be a multi-tiered system. The shallowest chamber lies about 5 to 10 kilometers below the surface and contains partially molten rock. Below this sits a much larger, deeper reservoir approximately 40 kilometers down that contains more fluid magma. The current dome appears to be primarily associated with activity in the shallower chamber. Seismic wave analyses indicate that portions of this chamber directly beneath the dome show decreased seismic velocities, a telltale sign that the material there has become less dense, possibly due to increased magma content or higher gas concentrations. Microgravity surveys, which measure subtle variations in gravitational pull caused by differing densities underground, support this interpretation. These surveys show a negative gravity anomaly beneath the dome, suggesting lower density material, potentially gas-rich magma or superheated fluids, has accumulated there. But what's actually happening in the chamber? Current evidence points to a process called magmatic intrusion, where magma from deeper sources moves upward, injecting itself into higher levels of the crust. As this magma rises, it releases dissolved gases, primarily water vapor, carbon dioxide, and sulfur compounds, which expand dramatically and create additional pressure. Dr. Carlos Ramirez, a magma dynamics specialist consulting with the USGS, explains, "Think of it like opening a soda bottle. As pressure decreases, dissolved gases come out of solution and form bubbles. In magma, this process creates a tremendous force that pushes against the surrounding rock. This process, called exsolution, can significantly increase the volume of material in the chamber without requiring a large influx of new magma. Temperature measurements from monitoring wells near the dome support this gas-driven model. Thermometers show increased heat flow, but not at levels that would suggest massive new magma intrusion. Instead, the pattern is consistent with pressurized fluids and gases migrating through the upper crust. Especially telling is the chemical composition of gases now emanating from fumaroles in the dome area. Analysis shows elevated ratios of carbon dioxide to sulfur dioxide, a combination typically associated with deeper magma degassing rather than imminent eruption. When magma approaches the surface before eruption, sulfur dioxide typically dominates. The precise configuration of the magma chamber also influences the dome's behavior. Geophysical modeling suggests the chamber isn't a simple blob of molten rock, but rather a crystalline mush, a semi-solid matrix containing pockets of more fluid magma. As pressure increases in these pockets, they can deform the surrounding crystal framework, working like hydraulic jacks to push the ground upward. Potential geological outcomes. With Yellowstone's dome continuing to rise, the natural question is, what happens next? Scientists have developed several evidence-based scenarios that could unfold in the coming months or years, ranging from benign outcomes to more serious events. Understanding these possibilities helps place the current uplift in proper perspective. The most likely scenario based on historical patterns is a gradual slowdown and stabilization. In this outcome, the forces driving the uplift reach equilibrium as pressure is redistributed within the magma hydrothermal system. The dome would stop growing and might remain stable indefinitely. This pattern occurred following several previous uplift events, including the significant 2004-2010 episode. Dr. Margaret Wilson, volcanologist at Montana State University, notes, "The Yellowstone system has demonstrated remarkable self-regulating properties throughout its monitored history. Pressure buildups often find release through existing fissures and hydrothermal pathways. A variation on this scenario would involve subsidence, the dome essentially deflating as pressure decreases. This could happen gradually over years or more rapidly over months, depending on how quickly fluids and gases find escape routes. Monitoring stations have already detected small areas within the larger dome where localized subsidence has begun, possibly indicating this process has started in certain sectors. A third possibility involves increased hydrothermal activity. As the dome creates new fracture networks in the crust, superheated water could find new pathways to the surface. This might manifest as changes to existing geysers and hot springs or the formation of entirely new thermal features. While dramatic, such developments wouldn't necessarily indicate increased eruption risk and could actually help relieve pressure in the system. More concerning, but still well within the realm of possibility, is a hydrothermal explosion. These localized but powerful events occur when superheated water flashes to steam underground, creating enough pressure to blast through the overlying rock. Yellowstone has experienced dozens of such explosions throughout its history, including the event that formed Mary Bay, a 1.5-mile-wide crater on Yellowstone Lake's northern edge, approximately 13,800 years ago. Modern hydrothermal explosions would likely be much smaller, but could still pose significant localized hazards. The scenario that generates the most public concern, a magmatic eruption, remains the least likely outcome based on current data. If such an eruption did occur, it would most probably be a relatively small event rather than a catastrophic caldera-forming eruption. Small to moderate eruptions have occurred within the Yellowstone caldera many times during its history, the most recent being a lava flow approximately 70,000 years ago. These events, while significant, are fundamentally different from the massive eruptions that created the caldera itself. Dr. Thomas Broadfield, a risk assessment specialist with the USGS, puts these scenarios in perspective. When we evaluate the current dome against Yellowstone's extensive monitoring record and geological history, we see a situation that warrants scientific attention but not public alarm. The probability of a major eruption remains extremely low, not significantly different from the background probability on any given day in Yellowstone's long history. Yellowstone monitoring systems. How do scientists know so much about what's happening beneath Yellowstone? The answer lies in one of the most sophisticated volcanic monitoring networks ever developed, a multifaceted system that keeps constant watch on the park's geological vital signs. This network serves as both an early warning system and a research platform, providing the critical data that informs scientific understanding of the current dome. At the heart of the monitoring effort lies the Yellowstone Seismic Network, comprising 46 permanent seismometers strategically placed throughout the region. These instruments detect ground vibrations as subtle as magnitude 0 earthquakes, tremors so small that only sensitive equipment can perceive them. The seismic network records approximately 1,500 to 2,500 earthquakes annually in Yellowstone, most too small for people to feel. Since the dome began forming, scientists have detected a 27% increase in tiny earthquakes within the Uplift zone, mostly ranging from magnitude 0.5 to 2.0, tremors consistent with rock fracturing due to increased pressure. Complementing the seismic detection system is the Yellowstone GPS network, which includes 24 permanent stations that continuously track ground movement with millimeter precision. These stations anchor directly into bedrock and transmit data via satellite to analysis centers where scientists can monitor displacement in real time. The GPS network first detected the current dome's formation in early 2023, when stations in the northeastern caldera began showing accelerated upward movement. Less visible, but equally important, is the park's hydrologic monitoring system. This network tracks changes in Yellowstone's legendary geysers, hot springs, and fumaroles. Automated temperature loggers record water and steam temperatures continuously, while specialized probes measure the chemical composition of thermal features. When the dome began forming, scientists noted significant changes in several nearby hydrothermal features. Old Faithful's eruption interval increased by approximately 7 minutes, while several hot springs in the Norris Geyser Basin showed temperature increases of 4 to 6 degrees Celsius. Satellite-based remote sensing provides the broadest perspective. INSAR, interferometric synthetic aperture radar, can measure ground deformation across the entire 3,472 square mile park in a single pass. These satellite observations, conducted roughly twice monthly, create detailed deformation maps that show the dome's extent and growth rate in vivid color patterns. Gas monitoring stations throughout the park continuously sample emissions from the ground, measuring carbon dioxide, hydrogen sulfide, helium, and other volcanic gases. These measurements help scientists determine whether the dome is being caused by magmatic processes or hydrothermal activity. Recent data shows elevated carbon dioxide emissions in the dome area, approximately 35% above baseline levels, suggesting increased gas release from depth. What makes Yellowstone's monitoring system particularly effective is its integrated nature. All these different data streams feed into the Yellowstone Volcano Observatory, where sophisticated computer models combine them to create comprehensive analyses of what's happening beneath the surface. When anomalies appear in multiple monitoring systems simultaneously, as occurred with the current dome, scientists can cross-validate their observations and develop more confident interpretations. Public safety measures. As Yellowstone's dome continues to develop, a natural question arises: what systems are in place to protect the public if the situation escalates? The answer lies in a comprehensive emergency management framework developed over decades, a system that balances scientific monitoring with practical safety protocols. The foundation of public safety at Yellowstone begins with the Volcanic Alert Level system maintained by the USGS. This standardized four-tier framework provides clear communication about volcanic threats. Currently, Yellowstone stands at advisory level, the second stage, indicating heightened unrest, but no immediate threat of eruption. If conditions were to worsen, the alert level would escalate to watch or ultimately warning, triggering increasingly comprehensive emergency responses. Behind these alerts lies the Yellowstone Hazard Management Plan, a detailed blueprint for action developed jointly by the National Park Service, USGS, and surrounding county emergency management agencies. This plan outlines specific evacuation routes, communication protocols, and response measures tailored to different types of volcanic and hydrothermal hazards. What makes Yellowstone's safety planning unique is its dual focus, explains Park Superintendent Regina Martinez. We need protocols for both unexpected, explosive events like hydrothermal explosions, which could happen with minimal warning, and for gradual escalations that might unfold over weeks or months. For immediate response to sudden events, the park maintains a dedicated emergency response team trained specifically in volcanic hazards. These first responders conduct regular drills simulating everything from hydrothermal explosions to ash falls. Their equipment includes specialized gas monitors and thermal imaging cameras that can detect dangerous conditions invisible to the human eye. Visitor education forms another critical safety layer. Since the dome's formation began, the park has updated its informational materials to include fact-based explanations of the current situation. Rangers receive regular briefings on the latest scientific assessments, enabling them to answer visitors' questions accurately without causing undue alarm. Communication infrastructure has been significantly upgraded to ensure reliable alerts even in remote areas of the park. A network of notification systems includes traditional emergency sirens, a text alert system for cell phones, and radio broadcast capabilities. These systems are tested monthly and can be activated within minutes if conditions change suddenly. For surrounding communities, county emergency management offices have developed specialized volcanic response plans. These include designated evacuation routes, shelter locations, and protocols for dealing with potential hazards like ash falls that could affect air quality and water supplies for hundreds of miles beyond the park. What's particularly noteworthy is how the safety system integrates with scientific monitoring. Automatic alert thresholds are programmed into monitoring equipment, ensuring that significant changes trigger immediate notification to both scientists and safety personnel. This integration minimizes response time between detection and action. Similar geological events worldwide. Yellowstone's dome formation, while unique in its specific context, is far from unprecedented in the wider world of volcanic systems. Examining similar ground deformation events at other volcanoes provides valuable perspective and potential clues about what might happen next. Perhaps the most famous analog is the Long Valley caldera in California, which experienced dramatic dome uplift between 1979 and 1984. During this period, the central section rose by about 45 centimeters, 18 inches, triggering significant concern. Scientists issued warnings, and some residents even evacuated voluntarily. However, after several years of intense monitoring, the uplift slowed without leading to an eruption. The Long Valley event taught volcanologists valuable lessons about how calderas can experience significant deformation without necessarily progressing to eruptive activity. A more recent parallel comes from New Zealand's Taupo volcano, which showed concerning signs of unrest in 2022. Ground uplift of approximately 12 centimeters was detected, along with increased earthquake activity, prompting authorities to raise the volcano's alert level. As with Yellowstone, the deformation appeared related to magmatic or hydrothermal pressurization beneath the caldera floor. After several months of heightened activity, the system gradually returned to background levels without eruption. Campi Flegrei near Naples, Italy offers perhaps the most dramatic example of long-term caldera uplift. This densely populated region has experienced several episodes of significant ground deformation, including an ongoing phase that began in 2005. The area has risen more than 4 meters, 13 feet, since the 1950s, in a phenomenon known locally as Bradyseism. Despite this substantial uplift, the caldera has not erupted since 1538. Demonstrating how volcanic systems can accommodate remarkable deformation without necessarily culminating in eruption. Japan's Iwo Jima provides another striking example of persistent uplift. This small island has risen more than 10 meters, 33 feet, in the past century through repeated dome formation events. While minor eruptions have occurred periodically, the island demonstrates how resurgent domes can develop over long timeframes without catastrophic outcomes. The Sierra Negra volcano in the Galapagos Islands presents a contrasting case where dome formation did precede eruption. Between 2005 and 2018, its central caldera floor rose by more than 6 meters, 20 feet, before finally erupting in 2018. This example illustrates how dome uplift can sometimes serve as a long-term precursor to volcanic activity, especially in systems structurally different from Yellowstone. What scientists find particularly valuable about these global comparisons is identifying which factors distinguish dome events that lead to eruptions from those that don't. Dr. Sophia Nakamura, who has studied caldera systems worldwide, notes, "The key differences we've observed include the rate of acceleration, the presence of certain types of earthquakes called long-period events, and specific gas emission ratios. So far, Yellowstone's current dome lacks several of the warning signatures we've seen in pre-eruptive domes elsewhere." Expert opinions and scientific consensus. How do the world's leading volcanologists and geologists interpret Yellowstone's dome formation? While some variation exists in their assessments, a general scientific consensus has emerged regarding the significance of the current activity and what it might mean for the future. Dr. Elizabeth Warren, director of the USGS Volcano Hazards Program, provides the official position. Based on current data patterns, we classify this as a significant but not alarming development. The uplift rates exceed historical averages but remain within the range of previously observed non-eruptive deformation events at Yellowstone and similar caldera systems worldwide. This measured stance is echoed by Dr. Michael Takahashi, who has studied Yellowstone for over 3 decades. What we're seeing is consistent with pressurization of the hydrothermal system rather than large-scale magma movement toward the surface. The seismic, deformation, and gas emission patterns all point toward a primarily hydrothermal driver with some deeper magmatic influence. Not all experts are equally conservative in their assessments. Dr. Vivian Rodriguez of the International Volcanological Association argues for heightened vigilance. While I agree an eruption isn't imminent, the acceleration rate of this dome exceeds what we saw in the 2004-2010 episode. Combined with the unusual location and accompanying seismic patterns, this merits classification as a more significant deviation from Yellowstone's baseline behavior than some colleagues suggest. When surveyed anonymously, a panel of 40 leading volcanologists provided probability estimates for various outcomes. Their collective assessment assigns a roughly 70% probability to the dome stabilizing or subsiding without major incident, a 25% chance of increased hydrothermal activity including possible small hydrothermal explosions, and only a 5% probability of any magmatic eruption within the next decade. Among those who considered eruption possible, most emphasized it would likely be a relatively small lava flow rather than a large explosive event. What generates strong consensus among experts is the value of the current situation for advancing volcanic science. Dr. James Chen of MIT explains, "This is a unique opportunity to observe a world-class caldera system during a significant deformation episode with modern instrumentation. The data we're collecting will refine our models of how these systems behave and improve our ability to distinguish between benign pressure adjustments and genuinely concerning precursors. Particularly noteworthy is how experts interpret the relationship between the current dome and Yellowstone's long-term eruption cycle. Dr. Sandra Williams, a specialist in supervolcano dynamics, contextualizes the current activity. When we consider Yellowstone's 2.1 million-year history, this event represents normal behavior for an active caldera between major eruptions. These pressure adjustments are how the system accommodates the slow accumulation of magma over millennia without frequent eruptions. Indigenous perspectives also offer valuable insights. Joseph Running Bear, a geologist and member of the Crow Nation whose ancestral territories include parts of Yellowstone, notes, "Our oral histories describe many periods when the Earth would swell and release steam before settling again. These accounts, passed down over many generations, suggest similar episodes have occurred repeatedly throughout human habitation of this region." Debunking misconceptions. In the age of viral information, misconceptions about Yellowstone's dome have spread nearly as quickly as the scientific data. These misunderstandings not only create unnecessary fear but can divert attention from legitimate concerns. Let's separate fact from fiction regarding some of the most common claims circulating online. Perhaps the most persistent myth is that the current dome signals an imminent supervolcano eruption that would devastate North America. This fear-inducing claim fundamentally misunderstands the timescales and warning signs associated with major caldera-forming eruptions. Dr. Rebecca Chen, who specializes in volcanic hazard communication, clarifies, "The current activity bears no resemblance to the precursory patterns we would expect before a catastrophic eruption. Such an event would likely be preceded by years of dramatically escalating unrest far beyond what we're observing now." Another widespread misconception suggests that government agencies are hiding the true danger from the public. This conspiracy theory ignores the transparent nature of Yellowstone monitoring. All significant data is publicly available online in near real time. The Yellowstone Volcano Observatory posts weekly updates and has no mechanism to conceal serious developments even if it wanted to, as hundreds of independent scientists regularly analyze the freely available monitoring data. Some social media posts have claimed the dome is rising feet per day rather than centimeters per year, an exaggeration that overstates the actual rate by approximately 10,000 times. Similar hyperbole appears in claims that thousands of earthquakes per day are occurring beneath the dome, when the actual increase amounts to perhaps 5 to 10 additional detectable micro-earthquakes daily compared to background levels. A persistent technical misconception involves Yellowstone's magma chamber, often described as a vast pool of liquid fire. In reality, geophysical imaging reveals that only about 5 to 15% of the chamber contains molten material. The rest consists of a crystalline mush, more like a sponge containing pockets of magma than a vast lake of lava. This physical state makes rapid, catastrophic mobilization far more difficult than many imagine. Some news outlets have incorrectly connected the dome to climate change, suggesting rising global temperatures are melting the magma chamber. This fundamentally misunderstands both volcanic systems and climate science. The heat driving Yellowstone's activity comes from radioactive decay deep within the Earth and the movement of tectonic plates, processes entirely unaffected by surface temperature changes measured in single degrees.